Welcome back, and now we're on to unit, the second portion of Welcome to Physics. So basically, you'll be learning about measurements and units, which is very important in physics. Okay, so why do measurements and units matter in physics? Measurements and units matter because they enable us to gauge, track, and compare information necessary for understanding this universe. Recording measurements give us insight, while stating units gives an idea of what is being measured. And I have a bunch of things that we use in our daily lives to take measurements. So here I have a scale to take your mass. You have your light bulb. You can measure the intensity of light. You have a thermometer, which can measure the what do you call it? Your temperature. Tape, which can measure length. Then you have atom to represent the measurement of mole. You have time, which is taken in seconds, and you have current, which is in amperes. Now, physical quantities. A physical quantity is one which can be measured. Physical quantities have numerical magnitude and unit. For example, in the picture, the mass of the long grain rice bag is 25 kilograms. Here, 25 is the numerical magnitude, which means size, and kilogram is the unit. It would be meaningless to state one without the other. Could you imagine if I just came and said, long rice 25? 25 what? Years? 25 what? Balls? So it's very important to always state a units whenever you are doing something. Okay? John took 25. You get what I'm saying? 25 what? What did he take? It could be 25 candies, 25 gumdrops, it could be 25 pieces of paper. So you always have to use your units. When kids don't use their units in my class, I often say 25 what? They give me a number, say it's 10. I'll be 10 kunomonos, so be careful. So a unit is a quantity chosen as a standard in terms of which other quantities may be expressed. There are two types of physical quantities: base quantities and derived quantities. Now there are 7 base quantities. You have length, mass, time, temperature, electric current, amount of substance, and luminous intensity. These are the symbols of these names on the left. Then these are the units used to represent these quantities. So if you're using length, the SI unit of length will be meters. If you're using mass, the SI unit of mass will be kilograms. If you're using time, the SI unit of time will be seconds, and the SI unit of temperature is kelvins, or it will be Celsius. The SI unit of electric current is ampere. The SI unit of amount of substance is the mole, and the SI unit of luminous intensity is the candela. So there are 7. Now the 11th General Conference on Weight and Measures held in Paris in 1960 adopted a worldwide system of measurements called the International System of Units, referred to as the SI system. And this is just so that we don't, that everybody will be standard in what they're saying, right? So you wouldn't have people from Sinky saying, I'm going to use pounds, even though we use pounds for weight, There's something very standard where we write in our lab books things for weight. We write kilograms or we write grams, depending on the size of the stuff that we're using. We wouldn't write pounds in our lab books. Now, in the physics, there are 7 basic quantities which use units based on the SI system, and they're depicted in the table on the right. The SI system is a modern form of the metric system, since it is convenient to use the multiples and fractions of the number 10. The SI system is the world's most widely used system of measurement. The US of A is the only industrialized nation that does not use it as its primary system of units for commercial activity, but uses it in the scientific fields. So they prefer to use the old time where you hear them talking about pounds, you hear them talking about old time units. I don't live in America, so I wouldn't really be quick on those things. Okay, so more times you see them using these basic quantities with their SI units when they're working in the lab. Like when you watch CSI, NCIS, and they're in the lab and they're doing the forensic science, you will hear them using these symbols because they're in the scientific field. They're not outside. Okay, from the 7 base quantities mentioned earlier, all other quantities are obtained. These other quantities are referred to as derived quantities, where their units are obtained from the base units via multiplication or division. So basically, these quantities are all derived. For instance, area. The unit of area, if you were to find the area of a square and, to find the area of a square, all the sides are equal, so it's just length times width. Each side will be the same. So if you have 2 meters for one side and 2 meters for the next side, 2 times 2 will give you 4 meters squared. So the symbol for area is meters squared. And so you see volume, the symbol or the unit for volume is meters cubed. For density, the unit for density is kilograms per meters cubed. For velocity, the unit for velocity is meters per second. Acceleration, the unit of acceleration is meters per second squared. And momentum, the unit of momentum is kilograms meters per second. And I have this section empty, and I would ask the children, which base quantity or quantities is this derived from? And you could just look at this and see meters. If you go backwards, you will see meters belong to mass. So therefore, area is taken from the base quantity mass. And the same thing for volume is meters, so it's taken from, length. See, I get mixed up easy. So it's taken from length. So area, which makes sense, because area length times width. So it's taken from the base unit length. Volume is taken from the base unit length. Density is taken from the base unit of mass and length, because mass has SI units of kg. Velocity is taken from where? Great, you said it. This is length and this is what? Time. And acceleration is from length and time. And momentum is from mass, length, and time. Great. So you can do this. And here I even went on further to bring more derived quantities, which I think you can do by yourself. Just look at the symbols. So basically we have these are the ones they would say they are named after famous scientists. They're not so as complicated as this the word here, but they are just named after famous scientists. And some of the unit symbols all have capital letters in these cases. For instance, force is named after the scientist Newton, and we use the big N, but it really means km over s squared. And so you can see the base units coming from that mass, length, and time. Pressure has units of pascals. Energy has units of joule. Power has units of watts. Frequency has units of hertz. And you can see per second here, and this comes from time. Electric charge has units of coulombs. Resistance has units of the ohm shaped like a horseshoe. Electromotive force has units of volts. Potential has units of volts as well. Our potential difference has units of volts. So what I want you to do is to answer these, and you tell me what you think should go in these boxes. Doom, 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 doom. Doom, 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 doom. Great. So from this you can see mass, time, length. For Joule you can see mass, time. For Watt you can see mass and time. For Hertz you can see time. For Coulomb you can see current and time. For resistance you can see mass, time, current. For electromotive force you can see mass, time, current, and the same thing for potential difference. So if you did that, kudos to you. Now we have some quantities that don't have any units. There are no units at all, and these are referred to as dimensionless quantities. So there are quantities that don't have units, and then you won't lose marks for writing them without units. For example, you have relative density, which doesn't use any units. There are no units for it. And the refractive index doesn't have any units. There's another one too. It's called magnification. Magnification doesn't have any units as well, because when you divide one entity by another, the units are the same and they end up canceling out each other. Okay, relative density, you divide in one density by another, comparing it to probably water or whatever it is at the time, could be mercury. Both of them would have the same units and so they cancel out. Okay, so that is why they don't have any units. So moving on to SI prefixes, multiple and submultiple units. A prefix is a word or set of letters that is used in front of another word to make a whole new word. For example, in the word unimportant, the prefix uses un, and the stem word is important. The words important and unimportant are two different words with very different meanings. So the multiples and submultiples of SI units can be expressed in terms of prefixes. The table on the right depicts some prefixes. These prefixes are often coined with basic or derived quantities. For example, kilometer, nanosecond, milligram, etc. Coining is done to express large numbers as smaller ones. For example, 1,000 kilograms is actually equal to 1 kilogram, right? So 10 to the 3 represents, if you look at this, 10 to the 3 represents, you just go on this map and you see 10 to the 3 represents kilo. So 1 kilogram, if you just, the kilo represents 10 to the 3 is equal to 1,000 grams. So if you look at this one now, 0.002 seconds is equal to 2. So if you want to write it in standard form, 2 times 10 to the negative 3 seconds, which is equal to 2 milliseconds, because 10 to the negative 3, if you look here, represents a milli. So you place the 10 to the negative 3 with the letter M to represent milli. And so 0.002 seconds is equal to 2 milliseconds. Okay, so you just replace it. And you have to learn all these right from top of tera right down to pica. So you have your multiples and you have your submultiples. So here we have tera, which is 10 to the 12, giga, which is 10 to the 9, mega, 10 to the 6, kilo, 10 to the 3, hecto, 10 to the 2, deco, 10 to the 1, deci, 10 to the minus 1, centi, 10 to the minus 2, milli, 10 to the minus 3, micro, 10 to the minus 6, nano, 10 to the minus 9, and pico, 10 to the minus 12. You need to learn every single one of them. Don't ask if they're going to give you on a test. They're not. I won't. So you have to learn them. So quantities are measured using instruments. The choice of instrument for a particular job depends on the size of the quantity to be measured and the range over which it might vary. An ordinary ruler is not the best instrument for measuring the thickness of a wire or the length of a cricket pitch or tennis court. Right? It's too short for in terms of the length of the cricket pitch and the tennis court. And it's too long in terms of the thickness of the wire. So a sensitive instrument responds to small changes in the quantity being measured, and an accurate one gives correct readings. These are very important. So you need a sensitive instrument and you need an accurate instrument. Scales that can weigh packets of sugar are not sensitive enough for weighing individual sugar grains. So all of these are important when you're deciding to take a measurement. For instance, let's talk in terms of relatability. When you go out, if you've ever flown out of your island, you would see that you have to weigh your luggage, right? It's a big scale, a massive scale, and so you put this luggage on it. If you had some sand and you put it on that scale, the scale is not sensitive enough to give you an accurate reading. So that's what we're talking about with sensitivity. The range on the scale that's measuring the suitcase is too wide. It's not going to account for the very small substances, the very light mass or little mass of the sand, right? And so therefore whatever you read on the scale will not be accurate. So now we're talking about linear and non-linear scales. What are linear scales? If you look at a ruler, how does a ruler look? It's straight. So linear scales are straight. And sometimes you will hear older people say, measure with a straight edge. It's pretty much they're telling you to measure with a linear scale, using a linear scale. And so what do you think are non-linear scales if linear scales are straight? Look at the clock. Yes, non-linear scales are scales that are not straight. They tend to be circular. They tend to be on an arc, like half a circle. So those are the types of scales. You see those scales every day on the clock. You see them on the speedometer for your car, on old-time cars that still have the analog clocks, the analog speedometers. You see them on those analog watches you wear. Some children don't know how to read analog watches, but they still wear them because they look fancy. So those are also non-linear scales. You see them on voltmeters, you see them on ammeters, you see them on galvanometers, if they are not digitized. So those are what you call non-linear scales. Errors that take place during an experiment are practical. Now, remember I told you that you'll be doing practicals, which are basically labs. And in these labs, we tend to ask, what could have limited you in this experiment? Or what precautions could you have taken? Or why do you think this experiment did not go as planned? Because sometimes some experiments we tell you exactly what to look for. Okay? And so it's in this, especially in chemistry, you hear you do two things and you're supposed to get this product and you're supposed to get 50% yield and you might get a 20% yield, and they ask you, well, what do you think you didn't get the 50% yield you were supposed to get? And so you will probably say due to human error, but then you have to expound a little bit more and say sometimes the material gets stuck to the walls of the glass, and you have to account for the fact that things get blown away and things of that nature. But here are three things that are very constant. They're constant variables in the lab. So you're going to read it. Every measurement is subject to errors. These can be due to one, the apparatus. Example, the scale of an instrument may be incorrectly calibrated. Believe it or not, sometimes instruments are incorrect, and that is the manufacturer's fault, is not your fault. And that is why it's good to always buy different types of instruments. And still again, sometimes this company may calibrate the instrument a little different to another company's calibration. So that may be a problem. That may be one of the problems. Next problem is the experimental conditions change. An example, a quantity such as temperature varying when it should be constant. In the labs that we have here, you may start your lab with the AC on, and then when you look, the AC stop working, and you continue the lab without the AC on, and now the temperature might screw your results. So instead, when you start doing thermal physics, there's nothing wrong with doing the lab in an AC environment, because when you go to American colleges and stuff like that, you're going to be doing labs in heated environments, because it might be cold outside with snow falling, and you cannot turn off the heat because you're going to die in there, and it might be a really really hot day with a turn on the AC, and you have to do your lab. Just make sure that the conditions are constant and you note them. So you said the AC was on at 25 degrees Celsius, and you note that, right? So you just make sure that the conditions that you execute the experiment in are constant. Not, oh, I start my experiment in AC and I feel cold, so I can just turn off, discontinue using the AC and continue doing the lab, and then all of a sudden you have all sorts of weird readings. Of course, because you were not in a stable environment. So you always have to try to make sure your environment is stable. The third one could be the experimenter, who is you, the scientist, right? For example, when an estimate has to be made of a reading between 2 marks on a scale, so you might misread the scales or misread the instrument. And the next one is errors arising from the first 2 causes may not always be easy to eliminate, but experimenters can reduce such problems by 1. Taking several readings of each quantity and calculating the average mean. And you could also avoid parallax. So make sure you always read directly on the line. So that is what I mean by avoiding parallax. When you're reading the ruler, don't read it from this side. When you're reading a clock, don't read it from this side. Always look head on at the ruler. Always look head on at the clock. And make sure you're not reading from this side. Otherwise, you're going to get wrong values. Okay? So that is how you would try to eliminate having errors. The first 3 errors, you take more than 1 reading. You can remember the first reading and always be a rough. That's the one where you're going to be like, oh my god, this doesn't look right. So take minimum 3, maximum, depending on the lab, would be 5 for me. You don't need to go any further than 5, because then you'll be wasting time. Remember, you only have about 40 minutes in class, so just hope the teacher gives you a time that makes sense. A set of readings, several readings. I don't tell you, make sure you do it 20 times. Oh my god, when are you gonna finish, right? So that's that, I think. Yes, and then we're gonna just move on into math in physics another day. Thanks for listening again, folks, and look out for my next video that will be on math in physics. It's not going to be just me reading to you. I'm going to actually have to carry out some math for you. Okay? Alright. Alright, thanks again, guys.